Hi, we're ProteinVision. We develop state-of-the-art models for protein prediction tasks, and we produce videos that explain the most important deep learning concepts and models in the field. In this video, we give a general introduction to protein language models, or short PLMs. We will focus on the basic ideas, what PLMs are, and why they work so well. In the next video, we will look more closely at how they are built and trained. So let's dive into protein language models. Proteins are linear sequences of amino acids, typically a few hundred. Each amino acid is a small molecule made of bonded atoms shown here in different colors. Hence, when a protein is synthesized, the sequence folds into a complex 3D structure that is made up of thousands of atoms. The structure of a protein defines its function. However, most of the information about structure and function is already encoded in the amino acid sequence. Protein language models try to capture this information directly from sequence without needing structural information for each protein. When processing protein amino acid sequences, we can use the same methods as for processing natural language. In natural language processing, we treat sentences as sequences of tokens. Most commonly, each token is a word or subword. A language model learns grammatical rules, meaning, and patterns in those token sequences. The arrangement of words follows grammatical rules and must result in a meaningful sentence. We can treat protein sequences in a similar way. A single protein amino acid sequence is the input for a protein language model, and the sequence is tokenized by splitting it into its individual amino acids. In this analogy, an amino acid plays the role that a word plays in a sentence. Similar to natural language, where the arrangement of words follow grammatical rules and must result in a meaningful sentence, protein sequences follow specific constraints on the arrangement of amino acids to result in a functional protein. Therefore, the same methodology that is used in natural language processing can be successfully applied to protein sequences. In a few moments, we will see that protein language models see millions or even billions of protein sequences and learn the grammar of proteins. For example, they learn which amino acids co-evolved and tend to appear together, which positions are conserved, and how patterns of amino acids relate to structure and function. Most modern PLMs are based on transformer encoders. In the next video, we will take a closer look at how transformer encoders work. Here, I will first give you a broad overview. Conceptually, a PLM does the following thing. It takes an amino acid sequence as input, for example, the amino acids M, K, W, and so on. The model converts each amino acid into a vector, a list of numbers that represent that residue. Here, the different color tones represent different numerical values. To update these vectors and to incorporate context about the remaining input sequence, transformer encoders let every amino acid look at all the other amino acids in the sequence using the attention mechanism. The different darknesses of the arrows show that different amount of information is extracted from different embeddings. This vector updating is done iteratively, and finally we have a refined vector for each position in the sequence. These vectors are called embeddings. They capture information not only about which amino acid is at that position, but also about its context in the sequence. Why does the context matter so much? Why do we need to incorporate information from the other amino acids into each amino acid embedding? The role of an amino acid in a protein depends strongly on its neighbors and on residues that are close in 3D space. Let us assume we have a linear protein amino acid sequence, where we divide all amino acids into being either hydrophobic or hydrophilic, meaning whether they like to interact with water or not. This sequence folds into a complex 3D structure, and most hydrophobic amino acids will be inside the protein core. A hydrophobic amino acid buried in the protein core has a different function than the same amino acid that is exposed to water on the surface. A protein language model learns to understand these differences by looking at the entire sequence at once. The attention mechanism of transformer networks tells the model which other amino acids are most important for updating the representation of a given position. Here we see, for example, the updated token embedding of the fourth amino acid, methionine. The embedding of an amino acid encodes not just I'm methionine at the fourth position, but it encodes more something like I'm methionine in this specific structural and functional context. But how do we learn the update functions? The embedding update functions of the transformer network depend on learnable parameters. To get useful parameters of our model and hence useful update functions, we need to train it for a task. The most common training strategy for protein language models is called mask language modeling. The core idea is randomly hide or mask about 15% of the amino acids. For example, in our protein amino acid sequence, we could mask the fourth amino acid, which is methionine. Masking means we replace the amino acid token by a so-called masking token, and hence we do not tell the model what amino acid we have at that position. Then we ask the model to predict which amino acids were masked, using only the surrounding unmasked residues as context. We can do this by using the updated embedding of the mask token as the input for prediction head, for example a simple multi-layer perceptron. The prediction layer outputs a vector with 20 entries, where each entry corresponds to one amino acid. For example, the first entry might correspond to the amino acid alanine, the second to K, which stands for lysine, and the last to methionine. For each amino acid we get a score between 0 and 1 that indicates how likely it is that we have a certain amino acid at that position, where values closer to 1 indicate that it is more likely that we have this amino acid at that position. In our case, we would input the vector at the fourth position, and we would then hopefully get a high score for methionine, which is actually the true amino acid at that position. So how do we train the model to predict the correct amino acid for the masked positions? For all the masked positions, we can create a binary vector with all zeros and a single one that encodes what the true amino acid is at that position. We then compare the vector y, which is the vector that we want to predict, with the vector y hat containing the predictions of our encoder. We compare the true and predicted vectors using the cross entropy loss, which tells us how far away we are from the desired prediction. For all 20 entries of the resulting vector y, we compute the product of yi with the logarithm of yi hat. Since only one entry in our vector y is non-zero, this entire sum will be simply a single multiplication of yi with the logarithm of the value that we predicted for the true class. So in our case, we get -1 times the logarithm of the predicted value for the methionine amino acid, which is 0.57. If we look at the values of the logarithm between 0 and 1, we see that for values close to 0, we get very negative values. Since we have a minus sign in front of the logarithm, this means that we get a very high loss. This makes sense because we want to predict a high value close to 1 for the true amino acid. And we see that when we do that, when we predict the value close to 1, the value of the logarithm is close to 0 and we would have a very small loss. As you probably know, during this training, we applied a protein language model not only to one sequence, but to multiple sequences at once that are part of a mini batch. We then simply calculate the average categorical cross entropy across the batch and across all masked positions in these sequences. Afterwards, we compute the gradient of this loss function with respect to each learnable parameter. Then we slightly adjust the parameters of the transformer network using backpropagation. These updates lead to lower loss values for the sequences that we have shown to the model. But this typically generalizes also well to proteins that the model has not seen yet, and hence the model learns general rules about the arrangement of amino acids in proteins. This training approach is called self-supervised training, because the model uses the input data itself to generate the data for this training task, and it does not require any external data to be labeled or measured. It only needs the raw protein sequences. But why is this self-supervised training, where we randomly mask 15% of the amino acids in the input sequence, a good approach to generate better and more meaningful representations of the amino acids in our sequence? To solve this task well, the model must learn which substitutions are tolerated at each position, which residues co-evolve, which means if one amino acid changes through evolution to another one, the other amino acid will likely change as well, because there's an interaction between the two positions. And the model also learns which amino acids are close in the 3D structure. Protein language models output one embedding vector for each amino acid. However, for most downstream prediction tasks, we need a single vector per protein of fixed size. When we use protein embeddings as the input for machine learning models, we typically want to have a single vector of a fixed size, independent of the sequence length of the proteins in our dataset. So how do we achieve that? There are two common strategies. The first one is mean pooling. We simply compute the average of all amino acid embeddings. This means we take the element-wise mean of all embeddings. More precisely, we average all the first entries in the amino acid embeddings to obtain the first entry of the full protein embedding, and so on. This gives one fixed size vector that summarizes the whole protein. Despite its simplicity, this works well for many global properties, such as predicting protein function or stability, and we don't need to adjust or fine-tune the pre-trained PLM. The second common approach is using a special so-called classification token. When fine-tuning a pre-trained PLM for a specific downstream task, we can add a special token at the beginning of the sequence, often called a CLS token. For example, we can put a prediction head on top of the classification token embedding and predict a property such as the optimal pH for the protein. The model then learns to store a summary of the entire protein in the embedding of this token. After fine-tuning, we can extract this updated classification embedding for each protein, here circled in green, as a task-specific protein-level representation. However, this only works if we fine-tune the model, and it is thus more expensive than simply using the mean-pooled embedding of the pre-trained model. Both approaches compress the information from all residues into a single vector that we can use for downstream prediction models. This was part 1 with a general overview about how protein language models work. In the next video, we will have a closer look at how the individual components of PLMs work.